Okay, next we're going to talk about describing relationships and learning some new language to describe the connections and relationships we're seeing in data. This will allow us to better understand what each others are saying if we have some common language and be able to describe these relationships. So we'll look at some examples that we looked at before and put some math language on it and then go from there. So first we're going to look at something called correlation. So a correlation is how deep or describes how that connection between data is made. So for example, here's a time versus distance graph, and you see all the points are along like this. And you'll see that they're all going in a positive direction. They're going up, okay? So that means as one variable increases, the other also increases. So in this case, as the time increases, the distance increases. So maybe someone walking away or information like that. So we say that this is called a positive correlation. And then naturally, when the connection is going down, and as one variable increases, the other one decreases, then we say that this is a negative correlation. So for example, the number of school days attended, as that goes up, as you go through more days at school, you have less textbook pages left in the textbook because you're going down. And then here's an example of no correlation. So it's not a positive or a negative correlation. There's no connection. There's no relationship, no connection between these data. And the example is like how long your hair is versus your math mark. There's no combination or connection between how long your hair is and what your math mark is. And so we say that there's no relationship and no correlation. So this is a positive, negative, or no correlation as a way to describe the relationship. You can also go a little bit further. So here's that distance versus time graph. And since we see a pattern in this data, we can draw a line of best fit. So I'm going to go and take my tool here and try and estimate a line of best fit. So something like that. Now, I think you'll agree that for this case, all of the dots are very, very close to this line of best fit. So the points are all clustered together, and we call this a strong correlation. It's when the points form a line that's almost perfectly in a straight line. Sometimes it is on a perfect straight line, but we can say this is a strong correlation. There's a big connection between the distance and time in this particular example. Now in this one, you can kind of see this is obviously a different scenario, still time versus distance, but the points are a little bit more scattered. Now I think you might agree that it's still kind of going up, and if we tried to draw a line of best fit, you know, it would be kind of something like this. But you see how the points are further away from the line of best fit and they're spread out. So we call this a weaker correlation. And the reason we want to separate the strong correlations from the weak correlations is if we were going to make predictions on these relationships, we'd want strong correlations. We'd have more confidence in our data when they're all very, very close together in this straight line versus something like this. So if I had to guess, you know, the distance at time 20, like way out here, I'd have a lot more confidence in my answer here versus a point here where it could be all over the place because the dots are a little bit more all over the place. So here's an example of a strong correlation versus a weak correlation. Okay, and correlation being the connection or the relationship that we're describing. So I know this is a little bit difficult to read, but it's okay. So we're talking about these. So here's an example. This scatter plot shows the height of a tree in meters over several years. So if I was to draw a line of best fit here, you know, it would come up and do something like that. So the height of the tree, you know, grows up like pretty similarly. This one describes the number of trees left in a forest after several loggers are cutting them down over a week. So in this case, you know, if we drew a line of best fit, it would be something like this, the number of trees less. And then this one is a little bit harder to draw a line of best fit. So let's go and describe each of these. So this one is the height of a tree over several years. So first off, is it a positive or negative correlation? Well, it's going up, so I would say it's positive. And would you say it's strong or weak? And personally, I would say it's strong because all the points are close to it. So I would say it's a strong positive correlation. And since it's positive, as the number of years increase, the height of the height also increases. As the number of years increase, the height increases. That's why it's positive, strong, because all the points are close. Okay, now look at this one. The number of trees left. So as the people are there, as the number of days go, the number of trees decrease. Okay, and because of that, I would say it's a negative correlation. And pretty strong, I would say. All these points are pretty close in a pattern, so I would say it's a strong negative one. Now this one shows the number of questions student did for math compared to the length of their shoelaces. So I don't think there's any connection between the number of questions and how long their shoelaces are. So for this one, I would say there's no correlation. You see the dots are all over the place and there's no pattern, no relationship, no correlation. So there's no correlation between these two. All right, so in summary of what we've done up until this point, we can just remind ourselves of the last day or last two, I think it was 2 days ago, where we were doing some comparison here. So remember that the hours of video games watched versus marks. So here we had the number of hours that certain people played on a video game and their mark, and we saw some sort of connection with that. So we saw that the scatter points showed some sort of pattern, some relationship. And so if there is a pattern, then we say there's a relationship or a relation between the variables. And then what we did is we drew a line of best fit. And if that line of best fit is straight, then we said that the relationship was linear. You recall another example we had where we drew a curve of best fit, and we said that was nonlinear. But if you can draw a line of best fit, then it's linear. And then if it as one variable increases, the other increases, that's a positive correlation. We just learned that. And if one variable increases and the other decreases, then it's a negative correlation. And this would be an example of a negative correlation because as the number of video game hours increases, your mark decreases. All right, so there's other things that we can use and other words we can use to describe linear relationships. So we first talked about linear and nonlinear, and just now we learned about positive and negative correlations and strong and weak correlations. But we can also describe them with something called continuous or discrete. So I'll read the definitions, but the examples will mean a little bit more. So if you decide to connect the dots or draw a line of best fit, the relationship is said to be continuous because it's possible to include all fractional or portions of the variable. So it's a little wordy. We'll see an example that'll better describe it. And then essentially the opposite of continuous is discrete, not continuous. So it's not possible to connect it, and you can't have portions of the variable. So let's try this example. All right, let's just look at an example here. So we're going to talk about the money earned babysitting. Okay, so let's say you earn $10 an hour. Maybe it's more than that, maybe it's less. I don't know. It's $10 an hour babysitting. Okay, if we were going to make a graph of this data, it looks something like this. I know it's really rough, but that's okay. So if you work 0 hours, you're going to get $0. 1 hour, you're going to get $10. 2 hours, you're going to get 20 and 30 and 40. Okay? So the question is it possible for you to earn, let's say, $15 babysitting? So if it was $15, it would be somewhere halfway between $10 and $20, which would be between 1 and 2 hours. Is that possible? Well, sure. You could babysit for an hour and a half and get somewhere in between there and make $15. You could probably maybe even make $17, you know, if you work closer to 2 hours, but not exactly 2 hours. Okay? Is it possible to get $22.50? Sure. All of these are possibilities. It may not be realistic. Like if the person gives you $19.29 for babysitting, you might say, hey, come on, give me 20 bucks. But it is possible because you can consider in between the points. You consider all fractions or portions of the variable. So we call this continuous, okay? And we would draw a solid line, okay? And that's straight. It would be straight. It's linear. But you can consider all the points in between the data. We say that that's continuous. So let's look at an example that might be opposite. So still about earning money, except this time you're selling chocolate bars. Okay, so let's say it's $3 a bar. Okay, you're selling them for a fundraiser. Your graph is going to look very similar. You know, it's going to go up and up and up, and in a straight line, just like this one did. But this you're making 0, and then $3 for one, and then $6 for two, and $9 for three chocolate bars, and so forth. The question on this one, can you earn $7 selling chocolate bars? Well, no, you can't, because 7 would be halfway between, well, not halfway, or somewhere between 7 and or 6 and $9. But you're not going to make 7. You're going to make $6 if you sell 2, and if you sell a third, you jump straight to 9. You can't, it's impossible to sell $7 worth of chocolate bars because you're not going to sell half or a quarter of a chocolate bar. Okay? So this is still a linear relationship, but we say that this one is discrete. Okay? It's, you can't consider in between or all fractions of it. So it's still a straight line. You can still draw a straight line, a line of best fit, but instead we make it dashed. And this tells the reader that you're only talking about discrete pieces of data versus this where you're talking about all the continuous pieces of data. Here you can earn fractional amounts of money earning babysitting, but you can't earn fractional amounts of chocolate bars, and so it's discrete. Next, we can describe the independent and the dependent variable. So the independent variable is the variable that is often used as the measuring stick in the relationship. It's always on the horizontal axis or on the bottom. The dependent variable is the one that reacts or changes as the independent variable changes. It's on the vertical axis. So when we're looking at a graph, the independent variable is on the bottom and the dependent is on the side, and the dependent depends on what the independent does. Another way that people have described this is the cause and this is the effect. So as something changes here, the dependent variable is affected by it. Okay? A good example of this is time. Time is almost always on the bottom. Okay, so you almost always have graphs with time on the bottom. And the reason is time is not really dependent on anything else. If you're measuring distance or figuring out how much money you have, time is going to go on independently. Okay, and the amount of money you make depends on how much time you work. Okay, or the height of the tree depends on what time is doing, how much time is gone. So time is almost always an independent variable. And examples of dependent variable are like money or distance. You know, how much money you spend or earned depends on the time. Okay, time's going to keep on ticking. It's independent of the money or the distance. But money does depend on how much time you've done. Distance traveled. Okay, so this distance you go, either traveled in some way or how far away you are from home or the bit or from your building, all of this depends on how much time goes. These ones react or change as this reacts. Okay, so the dependent ones along the side, independent on the bottom. Finally, we can describe something, relations between variables as direct variations or indirect variation. So direct variation begins at 0 and passes through the origin. There's no flat rate. And indirect is the opposite, where it begins someplace other than 0 and there is a flat rate. Again, an example is a better way to describe these variations. So let's think of sales and money earned. Okay, so if you sell nothing, you're going to earn nothing. Okay, you sell 0, you make 0. Right? The graph would look something like this then. You know, you start at 0, you make 0, you sell 0, you make 0. Okay, and as you start to sell things, you'll start to make money and the graph goes up. So this example has no flat rate. 0, 0. You start at 0. The flat rate, there isn't one. Okay, so we call these ones direct. You see it passes through the origin. So there you are right at the beginning and goes up. Okay, an indirect variation doesn't start here. So what's an example of that? What about our fare? So you know the fare example I use all the time. It costs $5 to get in plus $2 per ride. So the $5 is your flat rate. So even though you ride on 0 rides, you still have to pay $5. And there's this flat rate that starts up here. So we say this is indirect. It doesn't start at 0, it starts at $5 because you got to pay $5 just to get in, and it doesn't matter how many rides you ride, it's going to go up from there. So you can really see the difference as direct starting at 0, no flat rate. Indirect starts someplace else, there is a flat rate. Okay, so now let's look back at a bunch of the 4 examples here that we've been looking at and talking about all along. And I want us to now use this language to describe these. Instead of just saying it goes up or it kind of looks like this, we're going to use proper language to describe these. So you're going to decide, is the relationship linear or nonlinear? Do you have a positive or negative and a strong or weak correlation? Is it continuous or discrete? What are the independent and dependent variables? And then finally, is it direct or indirect? So let's think of that first example there, the hours of video games versus your mark. So remember, it was this graph here. So we drew a line of best fit, so we can say it's linear. Is it a positive or negative correlation? This one is going down. As you play more video games, your mark gets slower. And there's a pretty strong correlation with this, so we're going to say it's a negative strong correlation. The dots are very close to the line of best fit. Is this one continuous or discrete? So can we consider in between the points? So I think we had like 2 hours, 2.5 hours, and 3 hours. Could you consider 2.75 hours? Yes. Could you get a mark in between the ones that are there? Yes. So we say that this is continuous, and you can see that with a solid straight line. What about independent or dependent variables? So the independent variable is the one on the bottom. So in this case, it's the hours of video games. And the dependent variable is along the side, the y-axis, and that's the mark. So the mark depends on the number of hours of video games you watch. And then finally, is this direct or indirect? Well, where would this begin? It looks like the straight line would begin up here. Definitely not at 0, okay? And so it's indirect. Next, remember the speed of a stone dropped off the building? So it looks something like this, describing the speed. So we drew a line of best fit. It matches perfectly. It's linear. And I think it's safe to say it's a very strong correlation because it goes perfectly through all those dots. Positive or negative? Well, it's going up. As time increases, speed increases. So this is a positive, strong correlation. Is it continuous or discrete? Can I consider in between the points? So here's 2 seconds and 3 seconds. Can I consider 2.5 seconds? Absolutely. Can I have a speed in between 20 and 30? Absolutely. So I can consider in between those, so we call that continuous. And I've drawn a solid straight line. What are the independent and dependent variables? Well, independent, time. Almost always, remember, time goes along the bottom. And the dependent is speed. Speed depends on time, not the other way around. And finally, is this one direct or indirect? So where does it begin? Well, you can see that this graph begins at 0, 0. There is no flat rate, and it goes straight up. So we say that this is direct. Next, the distance fallen of the stone off the building. So that was the other example on the same day. The graph looked like this. Remember, we didn't draw a line of best fit. We drew a curve of best fit. So this is definitely non-linear, not straight. Would you say it's positive? Well, as time increases, does the distance increase? Absolutely. It's still positive, and our curve of best fit right through the points perfectly. So it's actually a positive strong correlation, even though it's nonlinear. Continuous, well, again, between 2 and 3 seconds, we can consider the distance. So yes, of course, it's continuous. Independent variables, time, always on the bottom, almost always on the bottom. It's the independent variable. Distance traveled or distance fallen would be the dependent variable. And finally, does this one start at 0? Yes, 0 seconds means 0 distance, so it starts at 0 and it's a direct variation. Finally, let's think of going to the fair. So we don't always need the graph. We can imagine what the graph would look like and still describe this relationship. So remember, $2 per ride, $5 to get in. So is this a linear relationship? Yes, it's going up by twos. You start with 5, and then it goes 7, 9, 11. It's going to go up by twos, and the first differences would all be the same. It's linear. If we would draw in a straight line, it would be linear. Next, strong or weak correlation. Well, it's definitely strong, and it's positive. As the number of rides increase, as the number of rides increase, your cost increase. So that's a positive, strong correlation. Is it continuous? Can you consider in between points? So for example, can you consider between 2 and 3 points? Well, no, I don't think you can. You can't ride a ride 2.5 times. And there's only a certain amount of money you're going to spend. So for example, if you ride one ride, you're going to spend $7. If you ride two, you're going to spend $9. Can you spend $8 here? No, that would be like 1.5 rides, and that can't do. Which means this would be a discrete relationship. What are the independent and dependent variables? Well, there's no time in this scenario, but you can imagine that the number of rides is the time. You're measuring your amount of money you're spending depends on the number of rides you ride. So the money or the cost depends on the number of rides. So you may not be considering it as time, but you can imagine that the number of rides could act like seconds. 1 second, 2 second, 3 second, 1 ride, 2 ride, 3 ride. And then the cost depends on the number of rides. And then finally, is this indirect or direct? Is there a flat rate? Yes, there's a flat rate at $5. And so you're going to go up by $2 every amount from there. And you're going to say it's indirect. 0 rides still costs you $5. So this one's going to be indirect. All right. So that's a great little example of how we're using this language and these new definitions to describe our relationships. And I'd like you to use this relationship for the rest of this unit as you're describing the relationships that we're learning. Now I'd like you to quickly try this describing relationship Google quiz. I think you'll find it pretty straightforward. It's based on the video you just watched. And so try this Google quiz. The link should be in your notes below. Okay, thanks. Good luck. Bye.